Okay, so let's start. So in this particular lecture, we'll look at a component which we call as dependent sources. So in the last lecture, we looked at analysis of circuits, and we saw that these circuits, they contain current sources and voltage sources. And we use the term independent sources in the sense that these voltages and currents had a value which was independent of any other circuit element. Whether it was an AC source or a DC source, the value of the voltage or the value of the current, it did not depend on anything else. It was independent by itself. So today we look at sources, voltage sources and current sources, which are dependent, which in the sense that they depend on the voltage or current across another circuit element. And so let's start by seeing why we need dependent sources. So as an example, let's say I have these strain gauge. So these strain gauges are basically resistors, and when you apply strain on them, in the sense that if you increase the dimensions or if you decrease the dimension, then as a result of strain, then what happens is that the resistance changes. And so by measuring the change in resistance, you can determine what the applied strain is. So in this case, for example, the strain gauge that we have here is the nominal value of the resistance is 120 ohms. So when you don't apply any strain, the value is 120 ohms. And of course, every resistor has some tolerance, so plus minus 0.3 ohm here. And as a result of the strain, so SG stands for strain gauge. And as a result of the strain, there's a change in the resistance. And the fractional change in resistance, delta RSG by RSG, equal to, let's say, as an example only, 1/50 multiplied by strain measured in percentage. So if I have 1%, let's say strain, so I put E equal to 1, and the fractional change in resistance is 1/50, right? So the goal is that, you want to measure strain, and for a variety of reasons, well, if you use these strain gauges properly, you can, for example, construct a weighing machine. And so a wide variety of purposes are there, applications are there. So what we want is convert the strain, which means E, into a number on a display, right? So this is, let's say, an LCD display, a liquid crystal display here, and a 7-segment display. And we want to display, let's say, the strain, or if you want, you can convert the strain into weight, and you want to display that on the LCD display, right? So starting from the strain gauge, you have to go towards the display. Right, so how do we do that? Well, what we could do is we could construct a very simple circuit. We could take, let's say, a 5-volt supply, use a resistor of 120 ohms. Why 120 ohms? Well, you'll see the reason for it a little later. So you have 120 ohms, and you have the strain gauge here, right? You have the strain gauge here. So this we are showing as a variable resistance. So as the strain E changes, the value of the resistance here will change. And let's say this is the voltage here. So obviously the voltage across it would be sensitive to the strain applied. So that's why we have made the circuit. So what we are trying to do is we are trying to convert the strain into a voltage. And we will take this particular voltage and then eventually transform it so that it can be displayed on the LCD display here. So V0 here is obvious. V0 is RSG divided by R1 plus RSG into VSS, the supply voltage here. So that's fine. So what we can do is, we'll not go into the details here. We can take the output voltage and we can add a block of circuits which we call as signal conditioning. So basically they will extract, we'll see a little bit more of it. They'll extract a voltage which is dependent directly on strain. Right now you see V0 has lots of terms here. So they will extract a voltage directly dependent on strain and do a couple of things on that particular signal so that it's suitable to be displayed here. All right, so all that we do with the signal, we are calling it signal conditioning, signal processing, signal conditioning. Okay, so let's proceed with this. So we saw that the fractional change in resistance of the strain gauge is 1/50 or 0.02 times E, the strain here. And V0 was given by this expression. So let's put this expression into the expression for output voltage here. So V0 will be at any a given point of time will be equal to RSG0 plus delta RSG. So what we are saying is that the strain gauge resistance is equal to some nominal value in the absence of strain and plus an extra value which is due to the strain. So RSG0, and we'll take RSG0 as same as we said. RSG0 was 120 ohms and R1 is also 120 ohms. So basically R1 and RSG0 are the same, right? So further let's simplify it. We can take RSG out here and we can take R1 plus RSG0 out here. So we get this expression here. So we are manipulating this expression to take advantage of this one here, that the fractional change in strain gauge is equal to 0.02 times E. We want to get a expression of V0 in terms of the strain here. All right, so we can substitute this here. We can substitute this as 0.02 E. And note that we said R1 and RSG0 are basically same. The value is the same. So this one translates to 0.01 E instead of 0.02 E here. There's a factor of 2 that comes in here. Okay, so we are assuming that the strain is pretty small. Note that it is 0.02 times E, and if E is, let's say, 1% or even smaller, these values are small, so we can take 1 plus 0.01 E in the denominator and we can express it like this, 1 minus 0.01 E here. And of course, the expression now is no longer exact, so we put an approximate sign here. Well, let's further simplify. Let's multiply them together. So we get 1 plus 0.02 E minus 0.01 E and then this particular term E square. And again, we'll make an approximation. We'll say that, well, because the strain is small, and look at this term here, E may be 1 or less even. So this term is going to be much smaller than the remaining two terms here, right? So we'll neglect the quadratic term. So then we can approximate V0 as 0.5 VSS into 1 plus 0.01 E. And then, let's remove the brackets and we can write it as V0 is 0.5 VSS plus 0.05 VSS multiplied by E. So what we see is that the output voltage consists of two terms. A term which depends directly on the strain. This is the term that we are interested in. And there is an extra term here, which is an unwanted term here. So this is the expression for V0. And we have a little bit of a problem. 0.5 VSS, so we've said VSS is 5 volt. So 5 into 0.5, so this is a fairly large voltage, 2.5 volt here. But we are not interested in this voltage. This voltage doesn't carry any information. It is this that carries information, and this can be pretty small because there's a 0.05 and strain, let's say, is 0.1%. So you put 0.1 here, you put 5 here. So you have a small term here added to a large term here. And what we would like is eventually on the display, we would like this term. This is the term that is of interest, and we would like to manipulate this and eventually display the information here. So this is causing a problem, right? So you have a large term here and you have a small term added to it, and you're interested in this particular small term, right? So what we do is we can address that particular problem by building a bridge kind of a circuit here. So what we do is, this is the original 120 ohms R1 and this is RSG. So what we do is we add another pair of resistors, R3 and R4 here. Both are 120 ohms. So what would happen is both are 120 ohms. So note that the voltage here, if you assume that there's, just assume for a moment that there's nothing between this node and this node here. Even though we have shown an amplifier connected, but assume that for a moment that this is like an open circuit. Amplifier, between these two nodes, there is a very large resistance or almost like an open circuit. So the voltage at this particular node will be basically 0.5 VSS. There's an R3 here and there's an R4 here and ground, right? And we're saying this is nothing. There's nothing connected here, right? So it would be 0.5 VSS. And now we define the output voltage or the signal voltage, which is the difference between this voltage and this voltage here. So this voltage we have already written. This voltage is here. 0.5 VSS plus 0.05 VSS multiplied by E. And the voltage here at this particular node is 0.5 VSS. So we can write now the signal voltage, the voltage between these two nodes, becomes simply 0.05 VSS into E. We have eliminated this particular part here. So the whole purpose of adding R3 and R4 was to generate a term equal to 0.5 VSS. And then we define the voltage, output voltage, as the difference between these two nodes here. and therefore we are able to eliminate it and obtain a signal which is simply directly proportional to the strain applied here, right? So now the unwanted signal, the large signal which was there, which was making it difficult to measure and determine what the small value here was, and now we've eliminated that large voltage here by taking the voltage between these two nodes here, right? And so note that we said the reason why we were eliminating this particular part was we were saying the signal. By signal, I mean a voltage or a current which carries information. So this is the part which carries information about the strain. So that's the signal here. And we said signal is small, right? Because if the strain can be small, and therefore the signal can be small. And therefore what we do is we take the signal and we apply to an amplifier. We apply to an amplifier, and the amplifier will take this weak signal, will amplify to a large voltage here. And this voltage here, we may, do processing of the voltage here. For example, we may take this particular voltage once it's large enough, convert it, this analog voltage here, DC voltage here, to a digital signal here, and then eventually use the digital signal to display the digits, the different digits here, which will tell us how much is the strain here. So, we said now, let's say you want to analyze this particular circuit, right? We have done an approximate analysis by assuming that that between these two nodes is almost like an open circuit, but in reality it won't be an open circuit. We've connected an amplifier, and so let's say we look at this particular circuit here, this part here. For the moment we ignore the signal conditioning part, and we want to analyze this particular circuit here, this part here. And remember, this is what we said about circuit analysis in the last lecture, that of course we have to apply KVL and KCL, but we need mathematical model of circuit element. So we have a new element here. We have this amplifier as a new element. The other ones we are familiar with, all the resistors and voltage source, but we have a new element here. And as we have shown, the new element is a 3-terminal. One terminal here, another here, and another here. So we have a new terminal, and obviously we need a model, because we need a mathematical model of this element. Otherwise, how do you proceed and analyze the circuit? Right, so the mathematical model of all the elements that are there in the circuit is important. And we have a new element here, an amplifying element, and we would like to know what the model of this particular element is. And until we do that, we cannot proceed with the analysis and design of this particular circuit here. All right, so let's look at this amplifier here. So we are saying we are applying a voltage between these two terminals here, and we are taking an output here. So now the amplifier is complicated, right? Inside it there may be several transistors, resistors, power supply, all kinds of things that are there. So what we are doing is determining a equivalent circuit model of the amplifier here. So basically meaning that if I look at it from the outside, external to the amplifier, then how does this amplifier really behave, right? So one of the ways in which we can describe this particular amplifier is by this equivalent circuit here. So what we are saying is, if you look at the amplifier between these two nodes and you look inside the amplifier, whatever is inside the amplifier we are not bothered, but the whole thing can be modeled. Now the word is important. It can be modeled as a resistor here that you see here, Rn. And from at the output side, the amplifier behaves like a resistor that you see here and a new element that you see here. New element denoted by this symbol here, and note that plus minus, so it's a voltage source. It's a voltage source, but it's a dependent voltage source. All right, so what we are saying is we are modeling the amplifier, this particular amplifier that you're saying. Now please keep in mind we are saying modeling. The amplifier inside has resistors, transistors, and all of that. We are not right now interested. We are saying from an external point of view, the amplifier can be thought of as consisting of a input resistance here, at the input side a resistor here, an output resistance here, this one resistor here, and a new element here. And a new element that you see here is say 4 terminals, 2 terminals here and 2 terminals here. So this is a new element here. And this new element is what we are calling it as a voltage controlled voltage source. So this is a voltage source, but it doesn't have a fixed value. It's not like 2 volt or 3 volt or whatever. its value is a voltage source, but its value depends on the voltage applied between these two pairs of terminals here. So as V in changes, the value of this particular voltage changes here. So that's why we call it a voltage source, but it's a voltage controlled voltage source. So the value is controlled by another voltage here. And in short, we call it VCVS, a voltage controlled voltage source. So to describe an amplifier, what we need is an input resistance, we need a voltage controlled voltage source, and we need an output resistance. So resistors are something that we are obviously familiar with. And so we need this particular element to describe an amplifier here, right? A voltage controlled voltage source. And so this is a new element for us. It's an example of a dependent voltage source here. Dependent because its value depends on the voltage applied here across a separate pair of terminals here. So let's quickly use this particular amplifier as a simple case. So suppose I have a signal which is weak, a small signal here, 1 millivolt. I attach it to my amplifier, one end here, the other end I ground, and I connect a load resistor of 1 kilo ohm. So I want to know, well, what is the ratio of V0 by Vs? If I apply 1 millivolt, how much voltage will I obtain here? So how do you analyze? Well, you substitute the model for the amplifier. This amplifier, we said, can be modeled by looking at it from the input side is a resistor. From the output side, it's a resistor plus a voltage controlled voltage source here, this part here, plus a output resistance here. And let's put some numbers. Let's say, this is just for the sake of analysis. Let's say this is 10K, this is 1K, and let's say the value of AV0 here is 100. So the voltage dependent voltage source is 100 times Vn. So to analyze this circuit, what we do is we take this symbol out, this amplifier out, and we substitute this circuit. And so we get this one here. So we have Vs 1 millivolt. Now between these two nodes, we have substituted the input resistance Rn, which is 10K. The voltage between here and here is plus minus Vn. At the output side, on this side here, we have a dependent voltage source, 100 times Vn. And then we put output resistance 1K here. And then we connected the load 1K here, right? And now we need to analyze this particular circuit. So it's sort of straightforward. Vin will be equal to Vs. And therefore, the voltage source here will be 100 times Vs. And then we have a voltage divider, 1K here and 1K here. So it's straightforward to write Vin equal to Vs, V0 equal to 100 Vn multiplied by 1K plus 1K here. So V0 by Vs is 50. So what we see here is that this particular circuit will amplify Vs by a factor of 50 here. Right, so we are seeing that amplifiers, to represent amplifiers, we need a voltage dependent voltage source here. And so this is a new element. When you're building complex circuits, you'll have amplifiers, and so you will encounter an element like this here, a voltage controlled voltage source here. Okay, so back to our circuit. So this was the Wheatstone bridge circuit here, and we have amplifier here to amplify the signal and signal conditioning here, right? And this is the model of an amplifier here. So let's substitute it back into this particular circuit here, right? So we take this amplifier out and we substitute it here. So we get this circuit here. All right, so keep this in mind. So we've just substituted this model here into this particular circuit here, right? And if you examine this particular circuit, you see that this part here is sort of independent. It doesn't depend on the rest of the circuit. The rest of the circuit, of course, depends on the previous part here, because we have a voltage dependent voltage source. So the source here depends on what happens here. But this part of the circuit is sort of independent, right, of the remaining part that you see here. And we can redraw this into this particular form here, right, as a more general form. So we have 4 resistors, and in between also we have a resistor here. So this is a circuit, Wheatstone bridge circuit, that you're well familiar with, and we analyze it, and when you all of you know, when it is balanced, then the voltage across V0 is 0. But if it is not balanced, then there will be a voltage across it. So we'll see that in at other places also, this Wheatstone bridge here. So the point is The point is that, we see that if there are amplifiers in my circuit, I need a voltage control voltage source here, a new element here. Okay. Well, let's look at another example, which is like an ideal transistor characteristics. So consider a following three-terminal device here. There's a terminal here, there's a common terminal here, and then there is another terminal here. And this is the input side, this is the output side, let's say. And just for the sake of discussion, we are talking about ideal. So let's say there is no current flowing in. The current is 0. And on the output side, the I0 versus V0 is interesting. I0 versus V0, if you look at it, the current I0 does not depend on V0. Whether V0 is, let's say, 0 or 1 or 2 or 3 or whatever, it doesn't matter. What does I0 depend on? It depends on VI, the input voltage here. So for VI1, one value of VI1, the current is here. For another value, the current is here. For another value, the current is here. And in fact, we can plot I0 versus VI, and I0 versus VI is, let's say, linear, right? So this is the nature of this particular element. Input current is 0. Output current does not depend on V0, but output current is sensitive to VI. So remember, in our discussion of triodes and transistors, we said output current is sensitive to voltage applied across another pair of terminals, so transconductance, while output current is not that sensitive to output voltage here, which is the output conductance. So these are like the transistor characteristics. This device has transconductance finite, but output conductance is 0, so obviously transconductance is very, very high compared to output conductance here. So this is the element, let's say, and we are saying that this is like an ideal transistor characteristics. So an element like this that you see here, which has these kinds of characteristics, I can represent it in this form. So from the input side, in this case, the current is 0, so we leave it as open circuit here. And from the output side, we are seeing I0 depends on input voltage. I0 depends on input voltage in a linear manner, but I0 is independent of output voltage here. So we represent it by this current source here, right? Again, note that dependent current sources have this diamond-like shape here instead of a circle or an oval here. And so this is a current source whose value is, let's say, Gm times Vi. And so it's a dependent current source. Why? Because this current source value is dependent on the voltage applied here. So we call this as a voltage controlled current source. So it is a current source, but its value is controlled by a voltage here, right? So voltage control current source, VCCS here, in short, voltage control current source here. And what we are saying is that this is like an ideal transistor's characteristics. In fact, if we look at a MOSFET, the MOSFET may look something like this here. Okay, so later on in the course when we discuss, we'll see that MOSFET, of course, MOSFET has this, complicated construction, but electrically, when you look at it from the terminal side, the MOSFET could be thought of under certain conditions to be like this here. Vi applied here, and V0 here, and I0 is Gm times Vi. So again, we see that in order to understand a MOSFET or a transistor and to use it in a circuit, we need a model, right? We need mathematical models of all the elements that are there in a circuit. And in order to model a transistor, well, we require use of a element called voltage control current source here, right? So these are, like, as I said, ideal MOS characteristics. So we can think of these four general dependent sources here. So in the first case, we have so all these dependent sources have four terminals. There's a terminal here, right? So which is the controlling voltage, and of course we have the source here. So we have a voltage source here, but is controlled by another voltage here, right? So this is a voltage control voltage source. In this case, we have a current here, and the current is controlled by a voltage, so we call it a voltage controlled current source here. In the next case, we have a current source here, so that's where CS is there, and is current controlled. It's controlled by current flowing between a pair of terminals here. And in the next case, last case, we have a voltage source here, but is controlled by a current. So it is a current controlled voltage sources. So we can have four dependent sources: VCVS, VCCS, current control, current source, current control, voltage sources here. And we've already said that these are amplifiers that we talked about. These are elements of amplifiers here, and we said that this one is like a MOSFET here, a transistor, a MOS transistor here. Some of you may recall that we could think of this like a it would be helpful in understanding maybe a bipolar transistor. If this is the base current and this is the collector current, let's say. Sorry, this one is F into I here. It should be F into I, not F into V. Okay, so correct that. So this is a current control current source. So F into I here, and similarly, this is H into I here, right? It's a current control. So the controlling value, this should be I here. Current control is a voltage source, but controlled by a current. So H into I here. And this should be F into I here, right? So these are there. So let's use this in an example. So let's say we have a circuit like this, and what do we have? We have a current source controlled by a voltage here. This is Vx. So we have a voltage controlled current source here, and we would like to solve this particular circuit. So the analysis of the circuit is similar manner. For example, we could say, let's say this particular node voltage is V1, and we could write KCL at this particular node here. So the current entering this node here is Vs minus V1 by 10. The current entering here is 0.1 Vx, and the current leaving here is minus V1 by 20. And the other thing we know is this Vx is Vss minus V1, right? So we can combine them together and we get a value of V1 equal to 8 and current equal to 0.4 amperes here. So once we have the analysis of this particular circuits consisting of dependent sources is very similar, except that these don't have a constant value, so they would depend on something else in the circuit. So this current source depends on Vx applied over here. Okay. So the other point is, if I make VSS equal to 0, what you would find is that you would find that there is no current flowing in the circuit, there is no voltage in the circuit. They're all zeros, even though I have a dependent source. So currents and voltages flow because of the independent voltages and currents. If independent voltages and currents are 0, the current elsewhere, everywhere in the circuit would be 0. You can work it out. If you put VSS equal to 0 here, short it, we'll find that, for example, Vx is 0 and all the currents, everything is 0 here. So you need an independent source, an independent voltage and current to cause current and power, current and voltage and all of that to happen there. This is another example. This is a equivalent circuit of a BJT amplifier. Note the word equivalent circuit. This is not the actual circuit of a BJT amplifier, but what we are saying is the BJT amplifier can be modeled in terms of this circuit here. And specifically, this is a model for a transistor here. And you can see here, this element is a voltage control current source here, right? 0.1 V. And our goal is to find out what is V0 by Vs, right? So we are saying that this is an amplifier, so you're applying a signal here and you're getting an output voltage here. So what is the voltage gain? V0 by Vs. So it's straightforward. We can take this part of the circuit. We can say V pi. So let's remove this V pi equal to Vs here, obviously. So then we know that this current source is 0.1 times Vs. It's 0.1, and this current source flows through a parallel combination of 100K and 1K. So V0 equal to minus because the current is flowing like this here, right? So it's flowing like this here. So this would be minus 1 V pi 100K into 1K. And V pi is Vs. So V0 by Vs is approximately 100K parallel 1K is approximately 100K itself, 1K itself. 100K parallel 1K is about 1K. 1K multiplied by 0.1, 10 to the power 3 into 0.1, so it's about 100. So the voltage gain is minus 100 approximately. You can of course compute the exact value also if you want. All right, so let's stop and sort of conclude that in circuits we'll also find dependent sources. And the origin of these dependent sources are they're being used to model amplifiers and transistors. So we have VCVS, we have VCCS, we have current control current source, and we have current controlled voltage source here. And please note the correction. This is F into I here again, and this is H into I here. So this is not H into V but H into I here, and this is also F into I here. And these are voltage, both of them are voltage controlled sources here, so both of them have V here, and in this case both of them should have had I here. But of course that's what happens when you copy and paste. You copy exactly from here to here and you don't make all the changes, so that's what you end up with, errors. It makes things easier but also maybe a little bit error. Anyway, so these dependent sources are very useful, and in many of the circuits that we will analyze from now on, you'll find maybe a VCVS somewhere there, or maybe a CCVS there, and you should not wonder where these things are coming from. These are being used to model amplifiers and transistors that may be there in the circuit. Okay, all right, so let's stop here.